Alright, as promised, a full walkthrough of the hanging hippo problem. We have a hippo hanging from two cables. One cable is making a 45-degree angle from the ceiling, or whatever point it is attached to, from the horizon, however you want to think about it. 45-degree angle there. And one of the cables is making a 30-degree angle with the horizon. And this tubby hippo weighs 3,000 pounds, which is the average weight of a male hippo, I believe. I'm pretty sure I Googled that last night. And we want to know what are the tensions in the two cables, which I'm going to call T1 for the tension in the first cable, and T2 for the tension in the second cable. So, to solve this problem, first, remember that we are dealing with vectors here, and as such, we need to think about all the different forces involved in this problem. Well, that hippo is a heavy, heavy hippo, and it is hanging, so gravity is pulling it downward, and we're saying that it's being pulled downward with a force of 3,000 pounds. Now, the hippo is in equilibrium, so we need to balance these forces. Well, we know we have the force going in that direction up that cable, and we have another force going in that direction up that cable. And these forces are somehow balancing each other out. So we need to think about this in terms of the horizontal and the vertical components of these vectors, because we know that the hippo is not moving side to side and it's not moving up and down, so everything has to be balanced. Now, when we were in class, we drew our triangles like this. We dropped an altitude from there, and we got two right triangles, one 30, 60, 90, and one 45, 45, 90 triangle. Now, people were upset because we said when you break these up into the two components, it makes it appear as if the vertical component of the vector T1 and the vertical component of the vector T2 have to be the same. That's not true, because we're not talking about the length of these pieces. We're talking about the tension in these cables. So although it seems like we're talking about length since we're dealing with sides of triangles here, we're actually talking about forces and tension. So yes, those two vertical components can be different. They don't have to be the same, which is why Mr. Henkla recommends drawing a completely abstracted force diagram to represent this, which is what I'm going to do. We have our equilibrium point in the middle, our hippo, and we have the force of gravity going down, which is 3,000 pounds. And we have our two cables, T1 and T2, those forces going to the side. Now notice I purposefully drew the vertical component of these vectors, which I guess I might as well draw in. So I've done this before, I don't remember where I left that sentence off, but notice I purposefully drew the two vertical components of our force vectors as different in length because they can be different. Don't think they have to be the same. Now, that being said, the horizontal components do have to be equivalent, and I'm looking at my drawing and they don't actually look like they are, so I'm going to fix that real quick. Okay, that looks much better, and that actually kind of looks like a 45, 45, 90 triangle now, and if you think about it, it makes sense that the two vertical components can't equal each other, because since the horizontal components have to equal each other, since our hippo is not swaying side to side, those pieces have to be congruent. Think back to geometry. Those two line segments have to be the same length. Well, that means in this triangle, 45, 45, 90 triangle, the two sides, the two legs of the triangle are congruent. But in this triangle, the 30, 60, 90, that vertical component has to be the smallest side since it's across from the smallest angle, 30 degrees, so it has to be smaller than that horizontal component, meaning it has to be smaller than the vertical component of our force in cable 2, tension 2, which I'm going to mark in. Okay, so I hope that at least clears up that confusion in class, and we can move forward with the actual problem now. So to solve this problem, we need to set up a system of equations. Now, to do so, we need to use these two key facts. We need to use the fact that our horizontal components of our force vector have to be congruent, since the hippo is in equilibrium, not moving side to side. And from that, if I label these, say, T1x and T2x, I can say that T1x has to equal T2x. Now, similarly, slightly different, but similar, if you think about the vertical components of this, the hippo is neither moving up nor is it moving down, and so the two vertical components of my force vectors from my cables, if I want to call that T1y and T2y, those two combined have to equal that 3,000 pound force of the gravity acting on the hippo. So from that, I can say that T1y plus T2y equals 3,000. And if you want to get really technical with it, we would start with T1x being negative and that 3,000 being negative, since we think of down as negative and left as negative. And we would really start with the equations, let's go T1y plus T2y plus, oh no, I'm running out of room. I'm trying to write plus negative 3,000 equals 0, because that is what it means for our forces to be balanced. It means they have a net force of 0. And then you can see I can just add 3,000 to both sides to get to that equation. Similarly with the other one as well. I'm going to pull that stuff out because we don't really need it. But it's a good thing to make note of and to keep in mind anyways. Okay, on to solving the actual problem now. We have the equations that we're going to eventually use to solve this problem, but they're incredibly generic right now. You know, they're just variables. They don't tell us anything. Let's make them more specific, because we want to find the tension in cable T1 and the tension in cable T2. So to do that, let's write the components of our vectors in terms of those lengths, T1 and T2. So look at the first triangle over here, that guy. We're going to look there first, and let's figure out that vertical component. Now, basic trig will get us that sine of 30 is going to equal the opposite side, which we have been calling T1y, divided by the hypotenuse, which is T1. Now let's get T1y by itself, and then that will be our expression for that side. To do that, you just need to multiply by T1 on both sides, and you'll get T1 sine of 30 equals T1y. And don't be confused here, that T1y, that is just the variable name that we are using for that vertical component. So I'm physically going to write that in for that vertical component, because that's way more useful than T1y. Now, in a similar manner, we can find the adjacent side of that triangle by taking the cosine of 30 and setting it equal to T1x over the hypotenuse, which again is T1. So just like before, multiply by T1 on both sides, and for that expression we will get T1 cosine 30. And think about it, that makes sense. Sine, we're talking about y values. Cosine, we're talking about x values. So it fits our current understanding of these ideas. And just like before, I'm physically going to rewrite that side as T1 cosine of 30. Now, I'm going to do the same thing with my other triangle, but now this triangle is going to have its components in terms of T2, the tension in cable 2. Now, I'm just going to skip straight to rewriting these because it's going to work exactly the same as it did on the last problem. Over here, I'm going to get T2 cosine, this time of 45, since that's my angle. And for my vertical component, I'm going to get T2 sine of 45. Right? Makes perfect sense. Okay, with that, I can now start to actually solve this problem. Remember, I said before, we're going to be using a system of equations to solve this. Not a complicated system by any means. Whoops. So let's go ahead and rewrite these two equations that we got with the new components that we found. So T1x, that was the horizontal component of our triangle on the left, and T2x was the horizontal component of the triangle on the right, the 45-degree triangle. So let's go ahead and fill that in with those values that we found. So we're going to get T1, I can't write, T1 cosine of 30 equals T2 cosine of 45. Now the second equation we're going to get is we are going to get T1 sine of 30 plus T2 sine of 45 equals 3,000. Cool? We have two equations and two unknowns, T1 and T2. So let's go ahead and solve this first equation for T1 and then substitute in. You could solve it for T2, doesn't make a difference. I'm just going to solve it for T1. So rewrite this, we will get T1 equals T2 cosine of 45 divided by the cosine of 30. Sweet! Now I'm going to take this value and I'm going to substitute it in for T1. So I'm going to get T2 cosine of 45 divided by cosine of 30 times the sine of 30. And all I've done, it looks messy, but all I've done is substituted in for T1 right there. T1 is T2 cosine 45 over cosine 30, and I have T1 times sine 30. So I have that. Plus T2 sine of 45, and that is still equal to our 3,000. Well, now I need to solve for T2. So to do that, you need to factor out a T2. So factor out that T2, pull it out front. What are you left behind with? You're left with cosine of 45 divided by cosine of 30 times the sine of 30 plus the sine of 45, and all of that equals 3,000. So to get T2 by itself, you have to take this whole big mess and divide 3,000 by it. So I'm going to cheat and be lazy since I am on a computering device, and I'm just going to move this stuff around and save myself some work. Divide 3,000 by all of that. It's messy, but honestly, plug it into your calculator like you see it. You can literally just go 3,000 divided by parentheses cosine 45 divided by sine 30 times sine, oops, wait, I'm messing up. And that should have said cosine of 45 divided by cosine of 30 times the sine of 30, and you don't even have to press any operation between those two, plus sine of 45, close your parentheses, and your calculator will tell you the number 2,689.726, which again represents T2, the tension in cable 2. Now that we have that, all we have to do is substitute back into our equation to find T2. So now I'm going to use that value I just found, 2,689.726, and I'm going to plug that directly in to the equation that I already have for T1. So, plug it in exactly like you see. T1 equals T2, which we found to be 2,689.726 times the cosine of 45 divided by the cosine of 30. Plug that into your calculator just like you see it, and you will get 21,000. Whoa, that's not how you write that number. 2,196.152. And again, that is T1. So we have done it. We have completed the problem. We found the two forces we were looking for. We found the two tensions, I should say, that we were looking for. The tension in cable 1 is 2,196.152 pounds, and the tension in cable 2 is 2,689.726 pounds. And we are done with the Hippo problem.